Hello again. This is Ty Newell, and for those of you who attended our webinar on 7 steps for designing an economical net zero home, I had too much information in too little time, and I apologize for that. We ended where we were working our way through using zeros and working our way through the different cases, and the remaining slides which summarize those results we did not cover. So this addendum is a follow-on that is not a live broadcast, but I'm just recording to work our way through the remaining slides. And so for those of you who watched the initial broadcast, then this one follows on that to help summarize that. As far as the slides, and again, these slides are all available, so you can get a copy of this. Where we ended, we had really just gotten to where we were moving through the zeros simulation model and seeing how to input values and how to find information related to the performance of these homes for the 7 cases. And in the remaining slides that I did not have time to cover, we'll discuss here. At this point, we're not so interested in zeros, but really in what these performance results for these 7 cases are saying. And even though the simulation is for a home in central Illinois, what I'd like you to know is that, as you use zeros for Miami, Florida to Anchorage, Alaska, from Wuhan, China to Istanbul, Turkey, you're going to find some similarities and you're going to find some differences, but overall you have the capability through zeros in order to examine those things. I will mention there are a number of international locations in zeros. As you scroll through the alphabetical listing of states in the U.S., then appended on the end are several countries, and we hope to add more as we move through. So if you have particular locations of interest, let us know and we'll try to add those. But we have Mexico, Turkey, Germany, United Kingdom, China, so a number of places, Canada. So check those out and let us know if there's any holes. And in any case, there's not that wide a variation of climates around the Earth such that you can most likely find something in North America. For example, Seattle, Washington, and Frankfurt, Germany aren't so far apart climate-wise, and so you might be able to do a pretty good guesstimate of some climates that we have included in that could match your local region. As we look at the results for these 7 cases that we covered, case 1, a conventional house with no windows, 6 inches of wall insulation, 12 inches of ceiling insulation, electric water heater, infiltration level of 7 air changes per hour at 50 Pascal blower door. We saw that we have about 12,000 kilowatt hours per year usage. This 2,000 square foot house, if we added 500 square feet of window in place of 500 square feet of south-facing wall, yes, the windows do drop the energy a bit by maybe 400 or so kilowatt hours per year. And when you look at the details in zeros, you see that about half that drop is by removing the wall, and the rest of the drop is the impact that the windows have. And so that's about a $50 a year impact as far as the cost. We'll see that coming up. If we take this case, initial case, and instead of putting windows in it, we just seal it up. No extra insulation, but we get out the caulk gun, we get out the tapes, and we seal it up. We get rid of natural gas and block all the flue vents, and then we put in a high quality ventilation system, something that automatically maintains air quality in the home. We see a much bigger drop in the energy performance of the house by sealing it up than we would by putting in a whole lot of windows on the south wall. When we go to this next case, case 4, in which we, in addition to sealing it up, we had a hybrid water heater, a heat pump water heater. And this house had 3 people, each using about 1,000 or a little bit more kilowatt hours per year to heat their 18 gallons of hot water per person per day. We see another similar large jump from this original case. And so we have 2 things that really aren't dependent on much other than caulking the house up and adding a good ventilation system, and then putting in this new technology, this hybrid water heater. The next drop, which is also substantial, but not as much as these initial 2, this would be puffing out the insulation a bit. In the case of 6-inch walls, if we could economically add at $5 a cubic foot more insulation in the walls, we'd find that the economic optimum, and we'll see that where the economics come in later, would take us from a 6-inch to about a 12 to 13-inch thick wall. And we'd also find that the ceiling insulation, which we originally had at 12 inches, that would go up to about 21 inches. The reason why ceiling insulation is thicker than wall is that it's less expensive. It's not because it's hotter up there. It's not because of something different in a ceiling versus a wall. Yes, there are some differences, but by and large, it's that you can blow insulation in the ceiling, and on a per cubic foot of insulation value, it's less expensive. It's in the range of about $1 to $2 per cubic foot, where dense pack, cellulose, styrofoam, or other, say, more rigid or self-supporting insulations you might put into a wall, these are going to be more like, say, $3, $4, $5 per cubic foot. And it's more difficult to make a wall thicker. You may have to add structure, which is an additional cost. So once we've sealed, put in today's technology for water heating, optimally insulated relative to our climate, about a 12-inch thick wall and about a 20-inch thick ceiling insulation. The remaining cases are adding solar to the house, so we don't see the house energy change. So as we move to this level, we're now looking at case 6, which is adding enough solar that we provide all the annual energy needs of the house. This case is the same case. We provide enough solar to supply the house. The difference we'll see in the economics, because this case represents what used to be true only a short time ago. 5-7 years ago, we were paying $4.50 per watt of solar PV installed. Now we're paying less than $3 per watt. And so when we explore the economics of that, that's where we'll see the differences. The final case, case 7, if we add another 3,000 watts to the 6,000 watt system, 3,000 watts results in enough additional energy that we're going to be able to drive about 12,000 miles a year in an electric vehicle. That takes us up to this level of energy, so we're a zero-plus house, now providing a large fraction of our transportation. And then this case is, again, $3 per watt solar versus $4.50 per watt solar. And we'll explore what that means as far as the technology. So house costs. When we just look at the upfront costs of getting the house built, what you're going to go to the bank and ask a loan for. Some of these changes aren't so significant. Windows is always an expense. It's the most expensive piece of a building's facade that you can add. commercial building, an institutional building on our campus at the University of Illinois, where I've been on the building committee. The windows cost $100 per square foot versus a well-insulated brick wall, which the A&E firm estimated at $50 per square foot. I mean, if that doesn't tell you only put in windows where you need them for view and where you need them for daylighting, I don't know what would. And in the case of a university, these are scholarships that aren't going to be made if we put expensive costs into fancy frills on the building. But this is what happens to the house cost. We assumed $45 per square foot, typical of a cost that many of you would see for today's good solar, good windows, good Energy Star level windows. You might see as much as $70 to $100 per square foot if you go to super windows, and you can for sure explore that with zeros. But the house cost goes up. Your mortgage is going to go up. If instead of windows or economizing on windows, you seal the house up and put in a fresh air ventilation system, you're going to add about $5,000 to the cost. If you, on top of that, add a hybrid water heater, a heat pump water heater, you're going to add maybe another $400 or $500 to the cost. If you optimally insulate, as we talked about, 6 inches of wall insulation to 12, 12 inches of ceiling insulation to 21, the costs go up some, but using the economic analyzer, optimizer in zeros, that this pays for itself over the lifetime. It lowers the life cycle costs. When we add solar, it does add costs. So you're going to have to ask the bank for more money. But when you go to the bank, you will be able to demonstrate through the financial engine in zeros that your monthly expenses have gone down. So this house really doesn't cost you on a monthly basis more than this house. The difference, you're asking the bank for more money, and the bank should like to loan you more money knowing that your monthly bills, because you have reduced your utility costs, that more money is going to them instead of being exported out of your community to wherever the utility is located. So that's an important part of zeros that that we hope you take advantage of. That instead of going in and just telling a banker how great your house is going to be, that you've avoided having thermal bridges and whatever other features you may have put into its design details. Here you're telling them dollars and cents. Look, I want to seal the house up. I want to add a heat pump water heater that you've never heard of. I'm going to add this much insulation. And then I'm going to add solar. But when you look at what I need to finance, I've stabilized my monthly bills. They're not going to jump from month to month like they used to in this home as the seasons change. I'm going to be healthier, and I've kept this in a range that I can afford relative to my income level. And you as a bank should want to make more money off of me, and so this is a good thing. Now as we go from $4.50 a watt to $3 a watt, wow, we see quite a nice drop in the house costs, and that's going to drop your mortgage. If we add 3,000 watts more of solar, our house cost goes from this level to this. Now it's higher than, quite a bit higher than the window cost, but with good advantage. The monthly cost has been stabilized and actually lowered. And with today's cost of solar, $3 per watt solar instead of $4.50 that we saw just a few years ago. As we look at what needs to be financed, even though this is adding a fair amount of cost to what we would have built with this conventional, my finances are much, much more favorable with this, and my life cycle costs for the lifetime of this house is much, much improved. Let's look at our utility costs. Case 1, no windows, typical construction, typical infiltration. Let's add 500 square feet of windows, about 25% window to floor space, about the most someone might be able to stick on a house, although I have seen people do more. We encourage people stay at about 10% window to floor area. 10% is more than enough for daylighting. For sure, you can blind as many people as possible with 10% window to floor area. You're going to be much more comfortable. The capacity of your heating and cooling system is going to be reduced, and you're still going to have more than enough window area for aesthetics, for view to the outside where views are nice. And so between no windows and heavily windowed, that's going to have a cost somewhere in here. And then these additional drops, sealing the house up, hybrid water heater, optimal insulation, the utility costs just keep tumbling down. And then finally add solar. And if it's just enough solar for the house, this is basically $240 per year. And as you look at the details within zeros, this is just a customer service fee of $20 per month. And so zeros allows you to account for that. If you add 3,000 watts more of solar for your transportation, as we discussed in the other one, solar-powered electric cars give you a price advantage of about 26 cents per kilowatt hour relative to today's fleet average cars with 30 miles per gallon. At today's gasoline prices, about $2.50 per gallon. And so this is a net savings, a negative, because the gasoline cost over a year for 12,000 miles of driving that you would save, that's roughly about $700 a year, and that more than pays for the $20 per year customer service fee. And remember, these are post-tax savings, so they relative to your salary per year, this is even better. Let's look at life cycle costs. So summarizing the 7 cases, the conventional case, no windows, conventional case, a lot of windows, and the amount of windows put in, probably somewhere in between $400,000 to $500,000 life cycle costs. We seal the house up. Yeah, it's a lot more energy efficient, as we saw, but the life cycle cost doesn't look so much different from the conventional with no windows. Why? Well, we added about a $4,000 to $5,000 smart ventilation system that keeps the house healthy, no matter how many people are in it, no matter what time of year. So this ventilation system is keeping the air healthy. We didn't have that here. And if you look at some of our other webinars or presentations or papers we've written, you'll see that people here are at best working at 90% of their cognition capability. People in this home are firing on all cylinders. Whether or not they make good productive use of that is another thing, but these folks are healthier than these folks. There's no ifs, ands, buts about it. So for the same price, you're going to be healthier and use a lot less energy. Now let's add a heat pump water heater. Again, it's more expensive than an electric water heater, but we do see a drop in life cycle costs. So this is a good direction to be going. We add in optimal insulation. That's dropping our life cycle costs. So we're continuing to nick away at the overall cost of this house on a 100-year basis. We add solar at $4.50 per watt. That's expensive. Now today's $3 per watt. Now we're seeing some really remarkable jumps in life cycle costs, from something between $400,000 and $500,000 to a life cycle cost that's now less than $350,000, about a $100,000 drop. We go to an electric car, $4.50 per watt solar, but now today's dropping below $3 per watt. Now we're at about $250,000 life cycle costs. Relative to $400,000 to $500,000, we've dropped about $200,000. This doesn't have the cost of the car, and as we talked about, electric vehicles have a bit of a premium. But from when I bought our electric car about 5-6 years ago, when that premium was about $7,000 to $10,000, that's now less than $5,000. Before long, tax credits will go away, but as automakers already know, these electric cars are going to cost them less to manufacture. So just like flat screen TVs, they're going to be able to sell them at the same cost as today's gas or combustion engine car, or a bit lower, but be able to expand their profit margin. But it just takes time to do that transition, to pay off their developmental costs, and then to get the manufacturing volume up so they get the same economies of scale. But it's happening, and we're seeing it every day move more and more in that direction. On the finance side, putting the 6 cases together, we started out with about $1,530 of monthly mortgage. We, for a conventional house, typical insulation, typical infiltration, leakage, poor air quality. We add a bunch of windows. We jump almost $200 per month in order to have about 25% of the floor area in window wall area. And this would scale somewhere in between. So if we had about 10% window wall area, our mortgage would maybe go up about $100 per month rather than about $200. Instead, moving over to a fresh air ventilation system that's amortized within the house and sealing the house up. Not much of a change as far as the monthly bill. As we saw, this had a much bigger, almost double the beneficial energy impact of south-facing windows. And then if we move on to a hybrid water heater, we, even with the addition of a more expensive water heater, we again see our monthly bills, mortgage, taxes, insurance, and utility drop again. Adding solar bumps our monthly mortgage cost up, and, this is moving into adding optimal insulation. The cost of the insulation moves our mortgage up. Over the lifetime of the house, this decreased our life cycle costs, and at the end of this mortgage, I have a 30-year mortgage assumed, and you can put in whatever mortgage lifetime as well as interest rate in zeros. But at the end of 30 years, then the benefits accrue because your energy bills are much less than what they would have been here. And so for the lifetime of the loan, you're paying a bit more, but once that ends, you reap the benefits over the next 7 years. And in homes, it's important to think beyond ourselves, that the decisions you're making, this life cycle cost decision, we're not going to last 100 years beyond when we build the house, but you're really making decisions for 4 to 5 generations of folks that may live in this home, and you're really trying to give them a say. But the good thing is that this is good for your pocketbook. This really should keep resale value as we educate folks more and more of the differences between today's energy efficient homes versus yesterday's not so efficient homes. As we add solar, the cost of solar does increase the monthly mortgage at the cost of just 5 years ago, but the difference between $4.50 per watt solar and today's less than $3 per watt solar, you're actually going to see your mortgage rate drop because of the competitiveness now of the grid equality between today's solar and what utilities are charging. And likewise, when you add in the additional bonus of not buying gas, instead paying for some solar to power a majority of your annual transportation for many folks. This goes up a little with $4.50 per watt, but today's less than $3 per watt solar. This cost, why wouldn't you do this? Your monthly rates are going to be down, your annual energy usage will be reduced, Your house is much, much healthier with a fresh air ventilation system. Everything's going in the right direction. The life cycle cost is $150,000 to $200,000 less than these conventional homes that people are building today. Why wouldn't you do this? It should be done. When we look at the capacity for heating and cooling that these homes needed, now we talked about the latent heat, and which is another factor, but just as far as design day heating and cooling, the no window house has no difference between a sunny winter day and a cloudy winter day, or between nighttime in the winter and daytime in the winter. So we would need about 6 kilowatts of heating, and this is about a 2-ton system, about 20,000 BTUs per hour. Not a large heating load. If we add 25% window area to floor area into the house, we see that on a sunny day, yeah, this house would use a little bit less, need a little bit less heating on a design day. But when it's cloudy or at nighttime, and and we've got data from homes that are windowed in this manner, I can tell you as soon as the sun goes down, the furnace goes on. The temperature inside drops like a rock, and I don't care how many tons of extra concrete you've dropped in, how massive your brick or stone chimney is inside, how much phase change material you've thrown in there, it will drop like a rock, because even though those might have some energy stored, you can't get them back out at the rate needed as you overwindow a house. So this house is going to require substantially more heating capacity than this house without windows. And cloudy days and cold days do go together. So this is going to happen. No ifs, ands, buts about it. As we move to a better sealed home and then a heat pump water heater home, there's kind of an interesting effect. Now you'll see online a lot of discussion about heat pump water heaters cooling the house during the winter, and all of that's a horrible thing, and that you just shouldn't consider it in areas where you have cold, harsh winters. That is absolutely false. It's a myth. It's based on no information, bad information. It just is not true. When you have today's high-quality heat pump, home heat pump space heating systems, cold weather heat pump space heating systems, coupled with an efficient heat pump water heater, even though this increase in heating capacity was needed to make up for the cooling effect for the heat pump water heater, this is a very, very modest increase. And in fact, you can see that this increase is much less than where our original case was with a standard water heater and conventional design. At the same time, as we go over to cooling, we're going to see that as we add a heat pump water heater in the summer, we're going to have a decrease in cooling capacity. Again, a fairly mild decrease in capacity, but a decrease. And so it'll go up a little here, it'll go down a little here. For sure, if you're in a place like Miami or Phoenix, all year you're going to see a benefit like this, and very little of the year will you see much of this. But in Vermont, and as I mentioned, our Vermont study looking at 13 identical homes, they all have heat pump water heaters, they all have served fresh air ventilation, they all have high performance, low temperature mini split heat pumps. These homes work in the harshest winter climates you find throughout the US and into much of Canada. There's no ifs, ands, buts about the performance. You can read about energy, you can read about comfort and indoor air quality. These homes absolutely work, and this heat pump water heater is a big part of that overall performance. So don't let anybody tell you differently. The most efficient solar-powered water heating system for a home today, and the most cost effective are solar PV panels coupled with heat pump water heaters in cold climates and in warm climates. So going on to then our final case, optimal insulation. Our final drop, yes, going to optimal insulation, we see a reduction in energy in both summer and winter. So our winter heating needs have dropped from nearly 6 kilowatts to about 4. And that's a drop in the size of the system that we need. And for a house without any windows, this is just flat because it doesn't matter if you have windows between a sunny day and a cloudy day. Again, with windows, you're going to have this difference. Without windows, and the reality of a house with some intermediate level of windows will be somewhere in between. Over on the cooling side, this is solar impact. Okay, besides even high-performance windows being lousy insulated walls, any sunlight that's let through a window is going to be an air conditioning load. So we go from, with no windows, needing less than a ton, about 2.5 kilowatts of cooling, to needing almost 3 tons of cooling capacity on a sunny day. And if you don't believe this, you know, just hop in your car with the windows closed after it's sat in a parking lot on a sunny summer day. A car is not a well-insulated compartment by any means, but for sure you'll get the full effect of what windows are doing on that, and it does that to your house as well. Over here on a cloudy summer day, this is not so much solar. On a cloudy day, you get about 15 to 20% of the solar radiation that you do on a sunny day. And so there is a little bit of solar coming in here, but really this impact is also because relative to, in this case, a 6-inch insulated wall, even the best high-performance window is not that well insulated. And then we see the changes in cooling capacity needed. You still need cooling capacity, but it is reduced from what the conventional leaky home would have required. On the latent side, and as we talked about with zeros, this is really a unique feature that you can schedule the monthly humidity level that you would maintain, and we kept the humidity so that it wouldn't drop below 19–20% in the winter. And based on that, that was showing that on the design day in the winter, to maintain about 20% relative humidity indoors, we would need about 5 to 6 liters of water vaporized, in addition to what human respiration is doing to add moisture. And a lot of this might be taken up with, depending on your habits as far as showering, washing, cooking, plants. We have about 40 to 50 plants in our home. They get about 6 liters of water, 6 to 7 liters of water per week. So about 1 liter per day for our plants, which is a nice way to humidify, a nice sanitary way to humidify. Over in summer, dehumidification, in order to keep relative humidity below 60%, we have to remove about 25 to 30 liters per water. Once we seal the house up, it drops a little bit, but we still need to get fresh air into the home, and that air coming from the outside has a moisture content that's mostly driving this, plus everything the human does between our respiration, perspiration, cooking, showering is adding moisture. So somewhere in the range of 25 to 30 liters per day is what's needed during design day type conditions. On indoor air quality, as Zeros allows you to view this, there's not much exciting going on among these different cases, because the leaky case, I intentionally picked 7 air changes per hour, which is 6 to 7 is about what we're seeing a number of contractors hit without any effort towards sealing a home up with today's construction practices. And with 3 people in a house, that is roughly the boundary where, on average, the indoor air quality would be at about, based on carbon dioxide, about something less than 900 parts per million in the home. Now, with smart ventilation that's actively sensing and bringing fresh air in as needed, and so as in zeros we modeled with the serve, and we had it set for 900 parts per million, I think, in the zeros modeling, that dropped us to something less than that, about 850 parts per million. The reason it's somewhat less is that zeros also looks at whether or not, relative to the smart ventilator, the outside is nicer than inside. And so for some months of the year, like in the spring and fall, it will bring in a bit excess air just because it knows that's better air to condition than the air inside the house. And so it doesn't just maintain it right at whatever set point you put in. It depends on the climate and whether it's beneficial or not to bring in some excess air. But zeros let you see where you are air quality wise as you change infiltration levels, as well as changing the ventilation level, whether you're using a smart ventilator or whether you're using an ERV or an HRV. Our current ventilation standards are set at a level where 20% of the populace, where that ventilation is basically assumed to be okay if 20% or less of the populace are dissatisfied with the air. The other 80% are not necessarily satisfied with it, but they're at least indifferent or okay with it. 20% dissatisfaction is a horrible number. We need that lower. And zeros will let you increase that level no matter what type of ventilation or leakiness you assume. But really, we do want this to be much less in order to have a much healthier home. Say somewhere where it's less than 10%, somewhere where we're maintaining on average something in, say, maybe the 600, 700, 800 parts per million of CO2 and associated VOCs. And this just follows, you get this information in zeros, but between the leaky home and then a smart ventilator that's maintaining less than 900 parts per million, that we're running on average about 100 to 120 cubic feet per minute of airflow. In the leaky homes, all the airflow is infiltrated air, and under some conditions, if there's not very large temperature difference between inside and outside, there's not very high wind levels, this could be very low, not sufficient. And then on windy days or when it's quite cold out and there's temperature differences driving infiltration, this could be very high. This does not mean the air is healthy, even though it says the average air quality is okay. Where you're spending your time and where this airflow is occurring in the house are two different things. Where these are systems, assuming fresh air ventilation systems that put fresh air where you live and extract them from the odorous and moisture areas like bathrooms and kitchens and mudrooms and laundry rooms. And so this is ensuring that where you live has fresh air, and so you don't want to assume these two cases are equivalent. They very much are not. Finally, on the solar side of things, we looked at a 6,000 watt system to supply this home with about 8,000 kilowatt hours of energy per year. And then we added 3,000 watts to that 6,000 watt system in order to supply enough for 12,000 miles of driving. As far as the physical size, here we had about a 450 to 500 square foot system, and adding enough for 12,000 miles of driving added another 250 square feet, really about the area of a garage roof, say a 25 by 25 square foot garage roof area. So really the space that the cars take up in the garage, if you add that much solar panel to the roof, that will give you most of those cars driving per year. And that's what these are intended to show, that scale. So we'll end up, and where I'd like to leave you is that I've been talking to you from this building, It was constructed in 1988. The previous owner, who used it for an art studio and created wonderful art, this piece of art that William Carlson created, is much more valuable than these solar panels. He's just a fantastic artist. But he was also a visionary in constructing this building. He went with the energy package that this steel building manufacturer offered at that time, and he put in a geothermal heat pump. It's the earliest geothermal heat pump system that I know of in our area. When we bought this building from Bill in the early 2000s, we continued adding insulation, and one of our newsletter articles describes our journey to put in new windows, improve the ceiling and insulation, and to finally move to a point where we added enough solar with Sunflower here, which is a 3.2 two-axis tracker, and then Sundial here, which is shown under construction but is another 5.5 kilowatt system. Between these two systems, we're now a zero-plus building. And if we can do that in this building, you can do that or make good strides toward that in an economical manner. So right now in our building, we're surrounded by this wonderful prairie, which is getting ready to bloom in a few weeks here. You should be able to make gains of this nature wherever you are in whatever type of building you're in. And we hope that Zeros will help you do that. So to end up, thank you very much for participating in these webinars. Again, sorry I packed so much into the previous one and just too much information and too little time as usual. We hope to follow up with additional webinars covering Zeros, explorations of different home features, from the size of the home to location to number of people and other facets of home design. But we hope this gets you kick-started in using Zeros. I think as you use it, as I've seen with many, many people, that you're going to get to where within 15, 20 minutes you can pop in the design features of a new home that you're exploring for a given project, and it's going to save you time. You as designers and builders and evaluators of homes, your time is much, much more valuable being spent on the details of making sure materials are there when a construction crew is there, making sure that quality is being put into the construction, making sure that you're buying materials that are good quality and cost effective. Adding another decimal point to the performance of a home is not going to be worth spending a lot of time on. And so we hope Zeros lets you screen through things that way. We also hope that Zeros lets you look at the economics of these high-performance homes and to be able to tell the story to your customers, to the bank, to the financiers of these projects, whether for a whole development or a single home, but be able to explain to them how each of these steps will make this an economically feasible home and one that's financially affordable, to dispel this myth that continues as the price of solar has dropped, as the ability to predict, and now that we've measured and validated these predictions, that this is reality. These homes are much more economical than conventional homes today. We're not waiting on anything. There's no technological barriers. So as you use Zeros, use that to help you tell the story, to start getting these homes becoming the mainstream rather than the exception. And finally, as we started out, this is the reason we're doing this. So let's push. It's good for our pocketbooks, but it's got importance much beyond that. Again, thank you very much for your time and for participating. Bye-bye.